In this video lecture, we will begin our discussion of metabolism and look specifically at phase 1 reactions. The learning objectives for this video are to describe the basic principles of metabolism, explain how cytochrome P450s and NADPH facilitate phase 1 metabolism, predict phase 1 metabolism reactions that will occur at common functional groups, evaluate how genetic polymorphisms will impact the metabolism of drugs and toxicants. Metabolism is the biochemical modification of drugs or toxicants by the living organism, usually through specialized enzymatic systems. The enzymatic pathways utilized for the metabolism of xenobiotics are not present for the purpose of metabolizing drugs. Instead, drugs utilize enzymatic pathways that are associated with the synthesis and metabolism of endogenous molecules like steroid hormones or compounds found in the plant matter that may be ingested. Metabolism typically converts the chemical compounds to more easily excreted metabolites by making them more hydrophilic, larger in size, or both. There are two types of metabolizing reactions, phase 1 and phase 2 reactions. The liver has the highest amount of drug metabolizing enzymes and has high blood perfusion rates, so it can quickly metabolize compounds that pass through the liver's blood supply. As we discussed in the absorption video, all content absorbed from the stomach go directly into the liver through the portal vein, where they undergo first-pass metabolism. Drug intoxicant metabolism also occurs in a lesser extent in the intestine, kidney, and lungs. In simple terms, metabolism is the modification of a chemical structure by the body through the use of enzymes. Depending on both the structural and functional groups present on the molecule and the enzyme present, will determine the potential product or metabolite of a compound. On a broad scale, the purpose of metabolic enzymes is to make compounds easier to eliminate from the body by making them more water-soluble. Tamoxifen is used in the treatment of breast cancer. This figure shows the many possible metabolites of tamoxifen present in the blood after administration. Take a moment to look at the different functional groups and how they are modified by different enzymes in the body into different metabolites. A drug or toxicant can be metabolized by a variety of enzymes and different pathways, which will determine how they will be excreted from the body. The metabolic enzymes are grouped into two categories, phase 1 and phase 2 enzymes. First, we will focus on phase 1 metabolism, which are typically an oxidation, reduction, or hydrolysis reaction. In phase 1 metabolism is a group of enzymes that unmask or introduce polar groups through oxidation, reduction, or hydrolysis reactions. These reactions can make a compound more or less biologically active. In fact, some drugs need to be metabolized through the phase 1 before they can become an active drug, like tamoxifen. In addition, for some compounds, metabolism can cause them to become toxic. Next, we will go through some enzymes that are commonly catalyzed phase 1 reactions. Cytochrome P450s are a group of enzymes that play a major role in phase 1 metabolism. They are all heme-containing monooxygenases that can catalyze the oxidation of organic substrates. There are a number of different P450 enzymes, and they all have a broad overlapping substrate specificities, meaning they can catalyze oxidation reactions of a number of different substrates. This pie chart shows the 8 P450s that contribute to metabolism of the highest percent of drugs. As you can see, CYP3A4 and CYP2D6 play a major role in drug metabolism. So let us go over a basic reaction catalyzed by a P450. We start with a drug, and this drug will be metabolized to a more water-soluble form. So we have oxygen in the form of O2, and through this reaction, one oxygen will end up binding to the drug, and the other oxygen will end up forming water. The hydrogens come from the NADPH, which is a reducing agent, leaving NADP, which will need to be regenerated for these reactions to continue. Cytochrome P450 enzymes can be found throughout the entire body. However, some tissues contain higher concentrations of enzymes than others. Comparing the cytochrome P450 content of the liver versus other sites of metabolism, you can see that in the liver, the total P450 content is 30 to 40 times higher than in any other tissue. There is a measurable P450 activity in the lung, kidney, and intestine, but the enzymes localized in these organs have little role in the metabolism of most therapeutic agents. However, they can be important in tissue-specific toxicities. Now let us go over a few common reactions catalyzed by P450 enzymes. First, P450s can add an hydroxy to a hydrocarbon chain. They can form an epoxide from a carbon-carbon double bond, and they can add an oxygen to a non-bonding electron pair of a nitrogen or sulfur atom. In addition, P450s can dealkylate both nitrogen and oxygen atoms and oxidize amines. There are additional phase 1 reactions that are catalyzed by enzymes other than P450s. Epoxide hydroxylase catalyzes the nucleophilic attack of water molecules on an epoxide to form a trans-diol. Here is an example of carbamazepine metabolism and the epoxide hydrolase-derived diol metabolite. In addition, there are other hydrolases that can catalyze other phase 1 reactions. Here's another example you may be familiar with, the metabolism of ethanol. When ethanol is consumed, it is predominantly metabolized in the liver by two reactions. First, alcohol dehydrogenase forms acetaldehyde. This is a compound that is responsible for the alcohol toxicity and the negative physiological effects associated with an alcohol hangover. Aldehyde dehydrogenase further metabolizes acetaldehyde into acetic acid, a common component of household vinegar. There are genetic polymorphisms in these two enzymes that contribute to individual differences in the speed of alcohol metabolism and the physiological effect of consuming alcohol, some of which are associated with certain populations. One common isoform of aldehyde dehydrogenase 2, which is strongly associated with some Asian populations, causes the enzyme to be inactive. This results in buildup of the toxic acetaldehyde, resulting in slower metabolism of alcohol, facial flushing, increased heart rate, headaches, and nausea. Genetic polymorphisms exist in a number of other metabolizing enzymes, such as cytochrome P450s, and are important to understand pharmacology. Typically, when administering a drug, the goal is to maintain a certain plasma concentration. Genetic polymorphisms in metabolizing enzymes can result in increased or decreased rates of metabolism. This top graph shows how plasma concentration levels change for an extensive metabolizer. The drug is mostly eliminated from the body by the time the next dose is given and may not be effective. However, when the same dosing regimen is used with someone who is a poor metabolizer, the drug may build up in the blood and eventually result in toxicity. This is an important consideration to keep in mind when designing and testing new drugs and when developing dosing regimens. Once a compound has undergone phase 1 metabolism, more of it may be able to be excreted through the kidneys. However, many products of phase 1 metabolism become substrates for phase 2 metabolism. In addition, parent compounds are directly metabolized through phase 2 reactions. In the next video, we will discuss the specifics of phase 2 metabolism. To test your understanding of this material, you should now be able to answer the following questions.